Hello, and welcome to my series on scheme theory. In this series, I will try to motivate the definitions of scheme theory and try and elucidate some of the algebraic and geometric structure of schemes and how it relates to classical algebraic geometry. The prerequisites for this series are a basic knowledge of ring theory and ideal theory, and a little bit of point set topology. If you don't have that, you can still try and follow along. You might still be able to gain something. To understand schemes, we must first turn to classical algebraic geometry. The setup is as follows. We have K, which is an algebraically closed field. We denote that by K equals K bar. That means that if F is a polynomial over K, then all of the roots of F are in K. So every polynomial decomposes as a product of its roots. Intuitively, the reason we want this condition is because we are interested in zero sets of polynomials. So we don't want missing information in the points of would-be roots of polynomials that aren't in the field. Also, historically, algebraic geometry originated with the study of polynomials and zero sets of polynomials over the complex numbers, which are an algebraically closed field, so this is a natural generalization. So we consider what we call affine n space, which is Kn, i.e. it's just n tuples of elements in K. And we sometimes, you will see this denoted in the literature as An over K. This means that we are thinking of it as an algebraic set, which we will define later. So we consider this space, and we're thinking of polynomials in n variables. So these are elements in f of k1, x1 up to xn. These are just polynomials in multiple variables. We will see examples a little bit later. So we're thinking of these as functions from kn to k, which are just given by plugging in a point into f. So if we have a point A in kn, we just consider f of a. So we want to study sets that are carved out by polynomials, i.e. when this is equal to 0. So for example, the set of all zeros of the equation x squared plus y squared minus 1 equals 0, well, over the real numbers, this just means that the distance of the point xy to the origin is 1, i.e. this is just a unit circle. I know we said we were talking about algebraically closed fields, but it's easier to picture this over the real numbers because we can't see in 4D, unfortunately. So this is also an example of a multivariable polynomial. Of course, we can also have cross terms, so x times y. More generally, we want to study zero sets of collections of polynomials. So more generally, we define an affine algebraic subset, or sometimes called an affine variety. Sometimes the definition of an affine variety is a little bit more specialized, but we'll get to that later. So let S be a subset of polynomials in n variables. Define V of S, which is a subset of affine n space, as follows. So V of S is the set of all joint zeros of polynomials in S. So all the points x in affine n space, such that f of x is 0 for all polynomials in S. Now note that for a point in V of S, we have that if f and g are in S, then their sum, f plus g of x, that is just f of x plus g of x, that is 0 plus 0, which is 0. So that means that x is also a 0 of f plus g. Similarly, if we have h, this is a multivariable polynomial, then h times f of x, that's just h of x, times f of x, this is also 0. So x is also a 0 of h times f. So multiplication by an arbitrary polynomial. These two things, closure under addition and under absorption, or multiplication by an arbitrary polynomial, tell us that we can pass to ideals. In other words, V of S, which is the algebraic set carved out by S, well, this shows us that it's contained in the algebraic set that is defined by its ideal, but you can check that actually it is equal to it. it's not hard to convince yourself that since S is contained in the ideal generated by it, i.e. the smallest ideal containing it, then V of the ideal containing it is contained in V of S. And now we proved the converse, so they're equal. We can refine this correspondence further, but first we will define the Zariski topology. So the Zariski topology is a topology defined on affine n space, whose closed sets are affine algebraic sets Vi, where I is an ideal of the polynomial ring in n variables. Now, you're probably used to defining topologies on open sets satisfying 3 axioms, but because of De Morgan's laws, open and closed sets, because they are the complement of each other, are dual. So if we show that these algebraic sets satisfy the axioms of closed sets, then these complements, which would be the open sets, would satisfy the axioms of open sets. So they would define a topology whose closed sets are these algebraic sets. So that's what we're going to do now. Verify as an exercise that following point. If I1 up to In are ideals, then the union of their algebraic sets is the algebraic set of their product. This shows that the algebraic sets are closed under finite unions. Secondly, if you have an arbitrary collection of ideals indexed by some j, then the algebraic set of their sum is the intersection of their algebraic sets. This shows closure under arbitrary unions. Finally, V of 0 is Kn, so Kn is an algebraic set, and the empty set is V of the entire polynomial ring, because there's constant polynomials which don't vanish on any point. So the empty set and Kn are both algebraic set. These are exactly the axioms of closed sets, and they are dual to open sets. So if you check De Morgan's laws, the complement of these VIs will satisfy the axioms of a topology for open sets. So we will get the Zariski topology. So the Zariski topology is quite weird. For example, it is almost never Hausdorffed. In fact, a lot of open sets are dense in closed subsets. In particular, if, for example, if you have an irreducible subset, which is not a union of 2 smaller closed subsets, then any open set which is non-empty is going to be dense inside of that. Nonetheless, it is very useful for reasoning and keeping track of the properties of varieties in affine space. For example, you have a correct notion of dimension. So now we'll give an explicit basis of open sets. If you recall, a basis of open sets is just a subset of the open set, such that every other open set is a union of some elements of the basis. So we think of the closed sets as just being carved out by families of polynomials. So now let f be a non-zero polynomial in n variables. We define the set df is the set of all points which are not zeros of f. This set is an open set, because if you note, it is going to be dual to the set it is going to be dual to the algebraic set defined by the ideal of f, because this is the set of points which f vanishes on, and this is the set of points which f does not vanish on. So now we show that this is a basis for the topology. So if we have some open set U of Kn, then this is going to be the complement of some algebraic set. So U is V of I complement. Then we have that the union over all elements of I of D of F is equal to U. So why is that? That's because being a point of U means that one of the polynomials of I does not vanish on U, so you are in one of D of F's, and conversely, every element that does not vanish on one of the polynomials in I is not in Vi, so it is in U. So if you didn't take that all in, maybe go back and try and reason through this. This is a basic point set topological argument, but it is very important that we have this basis of basic open sets, and we'll see that they're actually, they hold quite a bit of information later. So now we're going to show that we can actually go the other way. So given some subset, we can define what the ideal defined by that subset is. So we define a dual definition to what we define for algebraic sets. For a subset S of affine n space, we define the ideal defined by S to be all the polynomials which vanish on all points of S. So as an exercise, prove that this is in fact an ideal. So this is dual to our previous definition. So a natural question is, what is V of I of S? Because just because this is the set of all functions that jointly vanish on S, maybe the joint vanishing set is larger than S. So the maximal joint vanishing set would be V of I of S. So the question is, what is that? And it turns out that this is exactly the Zariski closure of S. So as a reminder, this is the smallest closed, i.e. algebraic subset containing S. In other words, it is the intersection of all closed sets containing S. So this is a theorem which we are now going to prove. So V of I of S contains S because it contains all the points that the polynomials of I of S vanish on, which in particular contains the points of S, and it is closed because it's an algebraic set. So it contains the closure because the closure is the intersection of all closed sets. So it is contained in every closed set containing S. Okay, now to prove the other direction, let X be an element of V of I of S. We want to prove that X is in S bar. So that means that if we have a closed set that contains S, X needs to be contained in that set. In other words, for all sets Vi containing S, X is in Vi. And indeed, this is true, so let F be a polynomial that vanishes on S. In other words, F is an element of one of these closed sets that contain S. Then, by definition, F is contained in the ideal generated by S. But X is in the vanishing set of that ideal. So all in all, we get that F of X is equal to 0. So, because this is true for every polynomial that is in a closed set containing S, this shows that X is in every closed set containing S, or in other words, X is in the closure. So this shows that V of I of S is equal to the closure, which is exactly what we wanted to show. In particular, if we start with an algebraic set, so if we have X is equal to V of J for some ideal J, and then we apply this V of I construction, so the closure construction, V of I of X, well, this is just the closure of X, which is X, because X is closed. So the closed algebraic sets are exactly those which V of I of them gives themselves. So that means that I is a right inverse to V on algebraic sets. So it is now natural to ask, what is I of V of J? So just as we ask what V of I is, it's natural to ask what I of V of J is, and also to find out which ideals J satisfy that I of V of J is equal to J again. Because once we find this family of ideals, these are exactly the ideals that come from algebraic sets. So these will be in bijective correspondence with our algebraic sets. So we have this correspondence between algebraic sets, which are actually sets X such that V of I of X is equal to X, and these ideals such that I of V of I is equal to I again. And we can go back and forth using V and I. If we find this class of ideals, then this will be a bijective correspondence. So V and I will be proper inverses, and this is an inclusion reversing bijection. So if we have X subset Y, then under I we get I of Y is a subset of I of X. The reason for this is that it's easier to vanish on a smaller set, so there's more functions on the smaller set. And conversely, if we have I contained in J, and we get V of J is contained in V of I, this is because it's easier to be a vanishing point of less functions. So the bigger your ideal, the smaller the amount of vanishing points is going to be. So now our goal is to try and characterize these ideals that come from varieties, i.e. I of X for X an algebraic set, and find out which properties ideals need to have to be of that sort. So, suppose that I of x is the ideal of some affine algebraic variety or algebraic set x. So, let f be a polynomial such that f to the n is in I of x, where here f to the n indeed signifies multiplication and not composition, because our ring operation is multiplication. So, then f to the n of x is equal to 0 for all x in I of x. But because we're over a field, this is equivalent to f of x being equal to 0 for all x in I of x, i.e. f is in I of x. So if a power of an element is in the ideal, then that element is in the ideal. These ideals are called radical. They are called radical ideals because they are equal to the radical, which we will define in a moment. So Hilbert's Nullstellensatz, which is a wonderful theorem, tells us that in fact this property alone characterizes the ideals that come from varieties. So they are exactly the radical ideals. So Hilbert's Nullstellensatz says the following: if we have an ideal I of the polynomial ring, then I of v of this ideal is equal to this square root of it, which is called the radical. So the radical is set of all elements such that for some power of n, if you raise that element to the power, it goes inside the ideal. In particular, note that an ideal is radical, i.e. if f of n is inside, then f is inside, if and only if it is equal to its own radical, if and only if it is equal to iv of I. So in other words, the radical ideals are exactly those that come from algebraic subsets. An important note is that now we know that if S is an arbitrary subset, then the ideal defined by S, by the Nullstellensatz, is equal to I of V of I of S. This is because I of S is a radical ideal. Now the proof of that is exactly the same as the proof that we gave before for I of X, for X an algebraic subset, but this means that this is equal to the ideal defined by the closure. So this ideal operation doesn't distinguish between sets and their closures, just like the V operation for defining algebraic subsets doesn't distinguish between subsets of polynomials and the radical ideals generated by them. Now, importantly, we also have the following corollary. I do want to reiterate that this corollary and the Nullstellensatz is only true in this formulation when the field is algebraically closed. So this is always the assumption that we have in the back of our minds, especially for this theorem. So the corollary is that maximal ideals of the polynomial ring are in bijective correspondence with points, i.e. just elements of affine n space. In particular, the correspondence comes from taking a point to the ideal defined by the point, which is this. So in particular, we are going to show that this is equal to the ideal of A, and we are going to show that this is a maximal ideal, and for a maximal ideal M, we will show that its vanishing set only has one point. So for the proof, let A be some arbitrary point. First, we prove that the ideal defined by A, which is just the ideal defined by the singleton set A, is this ideal MA, which is the ideal generated by the polynomials x1 minus a1, x2 minus a2, up to xn minus an. So we claim that this is the ideal of all polynomials that vanish on A. So, first of all, note that these polynomials, well, if I plug in A, I just get AI minus AI, which is 0. So these are all in IA, but this is an ideal. So by closure, under ideal operations, we get that by definition, this ideal MA, which is generated by these elements, is inside of IA. Conversely, suppose that we have a polynomial f that is in IA. Now, f of A is equal to 0. So we take the projection of f in this quotient ring, k of x1 up to xn, so the polynomial ring modulo MA. So recall that being 0 in the quotient ring is the same thing as being an element of the ideal. So we take this projection onto the quotient. Now, in this ring, because these elements are in the ideal, we have that xi is equal to ai in this ideal. So we get that this is equal to fa, which is 0. So we get that f is an element of ma. Now, if you want to see this a bit more concretely, we can also do that. So an alternative approach, so we have f and we want to prove that it's an ma. So first of all, we define this auxiliary polynomial g, which is defined by x, so this is defined by f of x1 plus a1 in the first slot up to xn plus an. So we take the polynomial f and we substitute in these variables. Now this is still a polynomial, so it has this form. This is basically a form of a general polynomial. It's just the sum over all of the possible combinations of powers of the variables plus these coefficients. Okay, so now if we do a substitution back, so if we take f of x1 up to xn, that's the same thing as g of x1 minus a1 up to xn minus an. But because we have this form of g, if we plug in xi minus ai, we get this polynomial. Now, note that all of the terms in this polynomial, so each of the summands, except the term c of all zeros, so note that this is the constant term, because this is the only term that doesn't have x1, x2, or and so on, because this is the only term in which the powers are 0. So all of the terms besides that one, besides the constant term, have some power of xi minus ai for some I. So they are all in this ideal. But notice that the constant term of this polynomial is exactly f of a. That's because if we plug in a into this polynomial, then we get that all of the terms that have at least one power of xi minus ai vanish, and all that's left is just the constant term, the one that didn't have any powers. So because f of a is 0, we get that f is again in ma. So these are two ways to show that this is actually the ideal that is defined by A. Next, we show injectivity of the correspondence. That is, we show that if we have MA is equal to AB for 2 points A and B, then A and B are actually the same point. So a maximal ideal can't correspond to more than 1 point. Now this is actually quite easy. So let A and B be arbitrary points, then for all I between 1 and n, we have that xi minus ai is in MA, but MA by hypothesis is equal to MB, and we just proved that MB is the vanishing ideal of B. So this shows us that xi minus ai vanishes when we plug in B. In other words, bi minus ai is equal to 0, so bi is equal to ai, so this is true for every I between 1 and n, so we get that A is equal to B. This shows injectivity of the correspondence. Finally, we show surjectivity of this correspondence. And if you think we forgot to show that MA is a maximal ideal, don't worry, we'll show that too. So, let M be any maximal ideal. First of all, we note that M is non-empty, so this is actually by the Nullstellensatz. If M were empty, then on one hand, I of V of M by the Nullstellensatz is just the radical of M, but maximal ideals and in fact prime ideals are actually always radical, so that's an exercise for you from the definition of prime. So this is equal to M. But on the other hand, I of the empty set is the entire polynomial ring. This is just because the polynomials that vanish on nothing are just everything. So we get that M is equal to the entire polynomial ring, which is of course a contradiction. Now let A be a point, which exists because this set is non-empty. We use the Nullstellensatz again, plus the property that the correspondence is order reversing. So we get that MA, which remember we showed is equal to the ideal of A, contains the ideal of VM. But again, by the Nullstellensatz, this is M. Now, here we'll note that MA is actually a proper ideal. This is because, for example, any constant polynomial can't be contained in it because constant polynomials never vanish, and this is a vanishing ideal. So, because M is maximal and is contained in a proper ideal, they have to be equal. So we finally get that M is equal to MA, and this shows the surjectivity. We associated a point to a maximal ideal, and we get for free that this proves that MA is maximal because it's equal to a maximal ideal. This lays the very basic groundwork for classical algebraic geometry, but keep in mind there's a world of definitions and theorems and theory that we have not discussed. So classical algebraic geometry can still be very powerful. We just introduced the basics to motivate modern algebraic geometry, and in particular, the study of schemes. This bijective correspondence between maximal ideals and points gives us a first idea of how to generalize the techniques of algebraic geometry to arbitrary rings. So just define a topology on the maximal ideals that mimics the Zariski topology, and then try and transfer the arguments. In particular, this kind of topology should make the maximal ideals of the polynomial ring behave homeomorphically to affine n-space using the Zariski topology. So you could start from there and try and define that topology more generally. So we'll explore this method next time, and we'll try and see if it works or if we need to do anything more, and we'll also try and motivate it further through coordinate rings and the view of a general ring as a coordinate ring on its maximal ideals. So that was the first video in this new series. If you're new here, I also do vlogs, and I also do a lecture series in non-commutative algebra, which is more scripted and much more formal. And I hope you stick around for the next episodes and learn some algebraic geometry with me. I'll see you next time.